This paper examines the gap between LLMs' performance on answer-based math competitions versus proof-based reasoning. While models like O3 Mini score well on competitions like Amy with numerical answers, their ability to generate valid mathematical proofs remains untested. The researchers conducted the first rigorous evaluation of LLMs on the 2025 USA Mathematical Olympiad, which requires detailed proofs rather than just final answers. The study involved testing 6 leading models, with results showing all models struggled significantly on these challenging problems. The methodology focused on creating a fair, transparent evaluation process. The researchers selected USAMO problems because they require rigorous proof-writing skills similar to the International Mathematical Olympiad. Each model attempted each problem 4 times to reduce variance. Solutions were anonymized and graded by experts who had either been on national IMO teams or participated in final selection stages. The judges developed standardized grading schemes based on reliable mathematical community resources, with each solution graded out of 7 points. They also documented specific failure modes to identify patterns in how the models approached these complex problems. Table 1 presents the main results, showing each model's performance across the 6 USAMO problems. The highest scoring model, R1, achieved only 2.0 points out of a possible 42, while Claude 3.7 scored 1.5 points. This performance contrasts sharply with these models' success on numerical answer competitions like AIME. Out of nearly 150 evaluated solutions, none received a perfect score on any problem. The cost of running these evaluations varied widely between models, from 0.42 for QWQ to over $200 for O1 Pro, showing significant differences in computational resources required for these complex reasoning tasks. Section 3 analyzes the patterns of errors in the model's solutions. Unlike human participants who typically know when they haven't solved a problem correctly, the models consistently claimed success despite fundamental flaws. The most frequent errors involved logical fallacies or unjustified reasoning steps. The researchers observed that models often treated critical proof steps as obvious without properly justifying them. Another key limitation was the model's tendency to repeatedly attempt the same incorrect solution strategy across multiple attempts, showing limited creative problem-solving ability. The bright spot was their strong performance on algebraic manipulations without external computational support. Figure 2 breaks down the distribution of error types across the 6 models. Logic errors, where models made unjustified leaps in reasoning, were the most common failure mode. Claude 3.7 and QWQ showed particular weakness in making unwarranted assumptions. The flash thinking model often attempted multiple solution strategies, but explored each one superficially. While algebraic errors were relatively rare, R1 showed a notably higher frequency of calculation mistakes than other models. The researchers also found that using LLMs, specifically O3 Mini and Claude 3.7, to grade solutions resulted in significantly inflated scores, showing these models cannot reliably evaluate mathematical reasoning. The researchers identified several interesting patterns in model behavior. Many models insisted on providing boxed final answers, even for proof-based problems, likely due to their training on answer-based questions. They also frequently overgeneralized patterns observed in small cases without rigorous proof. The OpenAI models, O3 Mini and O1 Pro, generally produced clearer and more structured solutions compared to more chaotic responses from models like flash thinking. Overall, the study concludes that despite impressive performance on numerical competitions, current LLMs have significant limitations in generating rigorous mathematical proofs, highlighting the need for substantial improvements in this area.